Okay, welcome to Michael Bronstein, our second presenter for today. Michael Bronstein is a professor at Imperial College London, where he holds the chair in machine learning and pattern recognition, and he's head of graph learning research at Twitter. He has previously served as a principal engineer at Intel Perceptual Computing and was one of the key developers of the Intel RealSense technology. Michael received his PhD from the Technion in 2007, and he's held research appointments at Stanford, MIT, Harvard, Princeton, and Tel Aviv University. Beyond academia and research, Michael is a serial entrepreneur and founder of multiple startup companies, including Nova Foray, Envision, acquired by Intel in 2012, Video Sites, and Fabula AI, acquired by Twitter in 2019. Today, he will be giving an exciting overview of geometric deep learning, and I'm excited to hear the talk. Welcome, and thank you for being here.
Thank you very much. Thank you, guys. And I'm very glad to be here, even though virtually. Thank you very much for the invitation. So today I would like to talk about what we call geometric deep learning, and a little bit of what is the history, what is the current state, and probably more interesting, what are the next steps and possible research opportunities. So the word geometric here is probably key, and let me try to explain in which sense I mean it. And for this purpose, let us make a step back, probably about 150 years ago. And if we look at the term geometry throughout history of mathematics, for about 2000 years, it was exclusively associated with Euclidean geometry. So the ancient Greeks invented geometry, so to say, and it was always the geometry that nowadays we call the geometry of Euclid, or Euclidean geometry. What happened in the beginning of the 19th century, it was really an exciting period for research in geometry, because a lot of different other geometries emerged. The construction of Lobachevsky, Bolyai, Gauss, and Riemann, they have led to the creation of non-Euclidean geometries, and it really evolved very quickly into a zoo of different geometries that were completely disconnected from each other. So researchers working on projective geometry, for example, were very different from those working on affine geometry. And mathematicians at that period of time questioned what actually defines a geometry and which geometry is more general. So the solution came from a young mathematician, Felix Klein, that was appointed as a full professor at the University of Erlangen. And he was asked to present a research prospectus, which he called a program, or the Erlangen program, as it is now called in mathematics, where he presented a quite radically new idea. So his idea of approaching geometry was the study of invariants, or quantities that are preserved under certain transformations. Sometimes we call them symmetries. And this allowed to exactly define which geometry is more general. He used the language of the group theory. For example, to say that under Euclidean isometries, rigid transformations, we have a lot of properties such as angles, distances, and areas that are preserved. Under affine transformations, we have properties such as parallelism that are preserved, and projective transformations are probably more general. Almost nothing is preserved. And this was really a very powerful concept and very powerful approach that made a significant leap in geometry, but also spilled into other fields. One of them was physics. So in physics, a stunning result by Emil Noether, what is called the Noether theorem, showed that any physical system has an associated symmetry. So you can derive conservation laws, such as conservation of energy, conservation of momentum. So some properties, some laws that were so far observed empirically by hundreds and thousands of experimental measurements, they could be derived from first foundational principles of symmetry. So conservation of energy, for example, could be derived from the symmetry of time, meaning that if you conduct an experiment today, tomorrow, or yesterday, the result will be the same. So a very intuitive notion. And in fact, then the invention of quantum mechanics and the different steps that have led eventually to what is now called the standard model were all based on these considerations of symmetry. And I'm citing here Anderson, who is a Nobel Prize winner in physics, that it's only slightly overstating the case to say that physics is the study of symmetry. So symmetry indeed plays a hugely important role in science and in many other fields. So let us turn our attention to machine learning. And I would argue that the situation in machine learning and in deep learning nowadays is a little bit similar to this zoo of different fields of study of geometry that existed in the period of Klein. And geometric deep learning is an attempt to some extent to systematize and unify them. So in geometry, if we look at maybe a simple setting of supervised learning, what we have is some high-dimensional data set of, let's say, images or any data points that are labeled, and we apply them on them some black box that is, let's say, a deep neural network that implements some function from the input to the output space. And for example, it assigns labels to different images. So what happens inside this black box? So if we look at the problem from the geometric standpoint, we immediately see that we run into the curse of dimensionality. So this is a phenomenon that can be explained from different perspectives. Let me show the geometric interpretation of it. So let's say that you want to distinguish between cats and dogs, and you do the most naive thing that you can imagine. So you take a sample of a cat, you open a small bowl around it, and you say everything that falls within this bowl will be considered a cat. So if your space, your feature space on the input of your black box is a low-dimensional space, like in this case, 2 dimensions, you see that the volume or the area that is occupied by this cat bowl is rather large. It's about 78%. If you go to a higher dimension in 3 dimensions, that's already about only 50%. But if you go to a higher dimension, let's say 10 dimensions, it's about 1.6%. So what we can actually write an analytic expression for the volume of a unit bowl in d dimensions, and we see that decreases exponentially with the dimension. And as a result, you can argue with a simple geometric argument that the number of samples that is needed to approximate a continuous function on d-dimensional input will depend exponentially on the dimension and on the accuracy with which you want to approximate it. So this is what is called the curse of dimensionality. It means that to approximate a function that, let's say, classifies a cat or a dog image will probably need more samples than the number of particles in the universe. So we're talking about humongously large, unimaginable numbers. So geometric deep learning essentially tries to take advantage of the geometric structure of the symmetry or the invariance of the data in the problem to make this problem tractable. And I know that I'm myself very skeptical about these bombastic, arrogant titles. I want to call it the Erlangen program of deep learning. And you know, when you hear this, you make somehow an implicit assumption that I try to compare myself to Felix Klein. So I just want to reassure that I'm trying to just take the idea, the approach of Klein of using the study of invariance as the underlying principle for machine learning problems. And we see actually, whether explicitly or implicitly, these principles in a lot of popular architectures that we deal with, starting from convolutional neural networks that exploit translation invariance on grids. And this was generalized to more general groups, for example, to make rotation invariance. And we can also talk about graphs, where the underlying principle is invariance to permutations, or manifolds, where this is gauge invariance or invariance under the choice of local frame. So today I would like to talk mainly about graphs, but just to give you an idea that this is part of a way bigger picture. So let's look at a very simple neural network. So this is perceptron, probably the instance of the first or one of the first artificial neural networks that were designed. And it acts by just making a linear combination of the inputs and passing them through a nonlinear activation function. So even with this simple neural network, if you connect 2 layers of such perceptron, you can approximate step functions. And once you can do it, you can approximate any continuous function to any desired degree of accuracy. So this is a property that is called universal approximation. And in a sense, it's a good result because it tells you that these networks are very expressive. But on the other hand, it doesn't. This inductive bias is very weak, so it doesn't contain a lot of structure. So you can approximate anything to any accuracy you want, maybe with a lot of parameters and a lot of neurons in this architecture. But when you apply this network to real-world problems such as image classification that I mentioned in the beginning, the fact that it is not aware of the structure of the data, that the pixels are not just elements of a vector, but they also have certain spatial organization, is actually the reason why it doesn't work. Because if I were to recognize this digit 3, for example, I can just pass it as a vector to the simple neural network. Now, if I shifted the same image by just 1 pixel, you will see that the input will be completely different, again, because we break the spatial structure of the pixels. As a result, we'll need to present the network a lot of examples or instances of the same digit with all the possible shifts in order for it to learn from the data these invariants to shifts. And this is obviously, it doesn't work. So the progress that was made in computer vision in trying to apply neural networks to images actually first was inspired by work in neuroscience, the classical experience by Hubel and Wiesel that brought them the Nobel Prize in the 80s. And the first manifestation or first realization of these ideas was in the neocognitron of Fukushima. And it already contained some of the basic building blocks of modern convolutional neural networks, which of course, probably the most cited paper in this field is the paper of Jan de Kanter, which is the culmination, so to say, of this principle. So if we look at convolutional neural networks, they take advantage of self-similar structure at different scales. So they combine local operations with shared weights, and basically this is realized as shift-equivariant convolutional filters. Combined with local pooling, it produces approximate shift invariance, and the weight sharing allows us to have a fixed number of parameters and linear complexity with the input size. And combined with the fact that it can be efficiently implemented on GPU, you get the recipe for the success of convolutional neural networks and why they revolutionized a field such as computer vision in the past decade. So let me show you a different example of data. So this is a molecule. It is represented as a graph. Here, each node represents an atom, and the edges represent chemical bonds. And if you wonder what it is, it's a molecule of caffeine. Probably many of you have had this morning. So if we were to predict some chemical or physical property of these molecules, such as atomization energy, we can try to apply the same idea. So we just stack let's say the features of the nodes into a vector and apply on it some simple neural network. The problem that now we have a very different structure here, because usually on a graph, you don't have a canonical way of ordering your nodes. So any permutation of the nodes would do, right? So here you can already anticipate that the kind of invariance or the kind of ambiguity will be very different. So we don't have shifts, we have permutations. And it appears that this kind of data that have graph structure is very prominent, especially recently with the emergence of social networks that are probably the most common examples of very large scale graphs with nodes being users and edges being different kinds of social relations and interactions. We see also a lot of biological networks such as interactomes, protein-to-protein interaction networks, gene regulatory networks, and so on. We see graphs maybe with some more structures in the form of meshes in computer graphics and computer vision, representing three-dimensional objects, and many, many more applications. So in 2016, I co-authored a paper that we called Geometric Deep Learning that tried to connect research in different fields where roughly the same ideas were invented and reinvented multiple times. So we didn't invent anything new in this paper, we just tried to systematize it and maybe cautiously proclaim that this is an interesting nascent field. And indeed now this term is used almost synonymously with graph representation learning and graph neural networks, but I hope that I convinced you in the beginning that there is more to it than just graphs. But today I would like to talk primarily about graphs. If I have time, I can say a few words about other structures such as manifolds. So one thing that you need to realize when you compare images with which we are probably much more familiar to graphs is that the structure is very different. So in images, if I look at a patch of pixels, I always have a fixed number of neighbors. In graphs, it's very different. So if I take a prominent user of a social network, he or she might have millions of neighbors, and some other more common user might have just a few tens or hundreds. Another thing that is important, that in an image we can fix the ordering of the neighbors. I can always, for example, talk about a pixel on the left or a pixel on the right. In graphs, this is usually not the case. We don't have canonical ordering of the neighbors. As a result, in images, we can talk about invariance to shift, and in graphs, we'll need to talk about more general invariance to permutations. So the three things I would like to try to do today is to describe how we can do something similar to convolution on graphs, how to do something similar to pooling, and how to do all this efficiently. So that will be the outline of the talk. Most of the time I would like to spend today. And then if I have time, I will try to show you some cool applications. So let's talk first about convolution. So I guess this is a concept that you're all familiar with in this way or another. To me, when I was studying signal processing in my undergraduate studies, the annoying thing was that convolution is just given you as a formula, you take it and you don't really ask questions why, where it comes from, why it is related to the Fourier transform and how. So let me try to explain to you actually how you can derive convolution from basic principles of invariance. Okay, so if you think of it as a neural network, so you have, let's say, n-dimensional input, n-dimensional output. So a convolutional layer looks like this. So if I write as a matrix the transformation, the linear part of the layer, the transformation from the input to the output, we have shared parameters. So each input is connected to a fixed number, each output is connected to a fixed number of inputs, right? In this case, just 3. And you always apply the same weight to, let's say, input I plus 1 or input I minus 1. Okay, so if I write it as a matrix, I get a matrix with this multi-diagonal structure. So this is a very particular structure. You can obtain it by taking a vector and stacking it into a matrix with shifts. So here we need to specify boundary conditions, and it's convenient to think of periodic boundary conditions. So it's a cyclic shift. So such matrices are called circulant, and in fact they are synonymous with convolutions. So you can represent any convolution as circulant matrix and vice versa. Now, one thing that is special about circulant matrices is that their multiplication commutes, unlike general multiplication of matrices. And in particular, if we pick up one circulant matrix, a special matrix that is called shift, basically it's a circulant matrix that shifts your vector by one position, right? So this is what is shown here. The circulant matrix commutes with shift. This is what we call Shift-equivariance. And it means that we can first apply shift and then convolution, or vice versa, the result will be the same. Okay. So another thing that we know about circulant matrices or commuting matrices in general, that they're jointly diagonalizable. It means that we can find a common eigenbasis that will diagonalize all circulant matrices. And it's enough to pick the eigenvectors of one of these matrices, and it's convenient to analyze the shift operator. So if we look at the eigenvectors of the shift operator, it turns out to be the Fourier vectors, and that's the first answer to the first question: where the Fourier basis comes from, the sines and cosines. These are the eigenvectors of the shift operator, or eigenvectors of any circulant matrix. So this is a very special basis, right? So as a result, convolution is diagonalized by the Fourier transform. So this is what we call the convolution theorem in signal processing. It allows us to do the convolution in the Fourier domain. Last piece of information, that the eigenvalues of all circulant matrices are different, and they're actually given by the Fourier transform of the vector that forms the circulant matrix. And this is exactly the convolution theorem. We can perform convolution either in the spatial domain by applying the circulant matrix to our signal, or in the Fourier domain by applying the Fourier transform, doing element-wise product by the filter, and doing the inverse Fourier transform. Okay, and basically the result will be the same. So what are the key insights? So convolution in spatial domain is circuit matrix. You can think of it as local aggregation on adjacent nodes of the grid with shared parameters. This special structure is due to the structure of the underlying grid. On the other hand, we see that all circuit matrices are diagonalized by the Fourier transform, which is the eigenvectors of the shift. And as a result, we can compute convolution in the frequency domain by applying the Fourier transform, element-wise product, and inverse Fourier transform. Okay, so if the filter is small, we can do it in the spatial domain by just sliding window, and this costs us order of n operations. If the filter is large, we can do it using the fast Fourier transform, which exploits the redundancy in the structure of this Fourier matrix. And this can be done in n log n operations, which is roughly as good as order of n. So when we move from grids to graphs, we can try to generalize both of these concepts. Okay, so let me say a few words about graphs. So graphs are collections of nodes that are connected by edges. So here, usually it's common to order the nodes, to assign to them some indices, but the crucial thing that you need to know about graphs that they don't have any order. So it's an unordered set of nodes, which in addition to which we also have a subset of the product of this set. So we have some either order or unordered pairs of nodes that are called directed or undirected edges. Okay, so the basic property of graph that you don't have an order of nodes. Once you order them in some way, you already assigned an arbitrary order. So that's why any permutation of the nodes would also be the same graph. Okay, so that's a crucial concept that we'll see recurrently throughout our discussion of graphs. So a neighborhood is just a set of nodes that are attached by edges to a node. And again, we don't have an order of our neighbors. So they can be permuted in any way. Okay, the number of neighbors is called the degree. So we will assume that we have some node features that will be d-dimensional vectors. So again, you can arrange them into an n by d matrix by prescribing some order of the nodes. So any permutation of this matrix will give you exactly the same structure, just under the different naming of or numbering of the nodes. We can also attach some features to the edges, or in a particular case, we can talk about weighted graph where these features are just positive scalars. So the structure of the graph can be represented as an adjacency matrix where at the position ij, we have a non-zero value if there is an edge from node I to node j. Okay, and if the graph is undirected, this adjacency matrix is symmetric. Now, another important construction that you see prominently in graph theory and signal processing and machine learning on graphs is the notion of graph Laplacian. So the Laplacian is a kind of local difference operator. What it does, it averages the values of features in neighbor nodes and subtracts this average from the node, from the feature at the node itself. So you can write it as in matrix vector form like this. So D here is the diagonal degree matrix, A is the adjacency matrix of the graph. And in a sense, it tells you how different you are from your neighbors. So it's a measure of smoothness of a signal on the graph. In physics, sometimes it's called the Dirichlet energy. And I should say that Laplacian is really a very fundamental construction. You will see it everywhere in mathematical physics, from heat equations to wave equations. And you can define Laplacian on a lot of different objects. You can define them on manifolds, where it's called Laplace-Beltrami operator in differential geometry. You can define them on meshes. You can define them even on metric spaces. So this is really a very, very fundamental construction. And unfortunately, I don't have much time to talk about it. So how do we do convolution on graphs? So again, we've seen two ways. One is using local aggregation in space on the nodes of the graph, and another one for the Fourier transform, which now is replaced by the graph Fourier transform. And the idea here is very simple. So if we look at the grid, right, we can think of it as a graph. So with periodic boundary conditions, this is what is called the ring graph. And if you look at the adjacency matrix of this graph, this looks surprisingly familiar. So this is actually the shift operator that we've seen before, right? So the adjacency matrix of the grid is the shift operator. And the key idea of going from grids to graphs is to use the eigenvectors of the adjacency matrix, or alternatively, you can also use the graph Laplacian as the analogy of the Fourier transform. So the two things are equivalent on grids because they are all circular matches. They have the same eigenbasis, but on graphs you will get somewhat different results. So if the graph is undirected, the adjacency matrix or the Laplacian will be symmetric. It will have orthogonal eigenvectors. So that's exactly the Fourier transform. If the graphs are directed, the construction is more elaborate. Allow me to skip it, and we'll see that at the end we'll not really care about whether the graph is directed or not. So this is how the Fourier basis or the eigenvectors of the ring graph Laplacian look like. So that's the classical Fourier basis of sinusoids of different frequency, but we can define it on any graph. So this is how it works on, for example, a rod network in the United States. So this already gives you a recipe to do convolution. So you can do convolution of X with W in the following way. So you apply the graph Fourier transform. So you project the signal X on your basis, on the eigenvectors of the Laplacian or the adjacency matrix that I denote here by phi. You apply the filter. So the filter is already designed in the frequency domain. So you operate with these coefficients, the spectral coefficients of the filter, W hat. And then you apply the inverse graph Fourier transform, again multiplying by phi. So far it's exactly like what we had in the Euclidean domain. So the bad news come from the computational complexity. So now we don't have any redundant structure. In general, we don't have FFT on graphs. So the cost of multiplying by these dense matrices is order of n squared. And this is just the multiplication. Computing the eigenvectors will cost you maybe slightly less than n cubed. And the same thing goes for the inverse Fourier transform. So if we compare to the classical case, the complexity is squared as opposed to n or n log n. The number of parameters also, these spectral coefficients of the filter, it's order of n as opposed to order of 1 that we had in classical convolution with shared weights. There is also no guarantee of spatial localization. We designed the filter in the frequency domain. The filters are isotropic. I will say a few words about it in a second. And probably what is even worse, that the filters are basis dependent and they don't generalize across graphs. So let me talk about this thing of basis dependence. So if I have a signal that is defined on a graph, in this case it's a mesh which has some extra structure, but the idea is the same, and I apply some spectral filter, if I perturb now the domain, the underlying mesh, I will have a different graph, a different Laplacian or different adjacency matrix, different eigenvectors. If I keep the same filter coefficients, I will get completely different results. So it means that the filter is unstable when it's done in this way. So the second thing that was troublesome is that the filters are isotropic. In this has to do with the fact that on grids, we had a canonical order of vertices. On graphs, we don't. So as a result, any construction, such as the Laplacian, for example, is agnostic to permutations, to the ordering of the neighbors. So the Laplacian, by virtue of averaging the neighboring nodes, is completely unaware of their order. So if I were to apply this kind of filter on a grid, I will see, for example, in two-dimensional grid concentric circles. They're oblivious to directions. On meshes, the situation is more optimistic because we have only rotation ambiguity. So I can pick up the first node and then order all the rest in, let's say, clockwise orientation. As a result, we can do directed filters. So the different approach that I can take to convolution on graphs is to think of convolution as some kind of spectral transfer function that is applied to the Laplacian or the adjacency matrix. And here, when I say that I apply a function to a matrix, I mean that I apply it to the eigenvalues of this matrix. So if I interpret eigenvalues as frequencies, this is exactly the spectral transfer function or a filter. And if I can express this function in a parametric form with fixed number of parameters, I get rid of this problem that I have a number of parameters that is dependent on the input size. And if I express this function in terms of simple matrix operations, I can avoid the explicit computation of the eigenbasis. And in some cases, I can also guarantee stability under graph perturbation or some form of localization, or at least some sufficiently fast decay. So the simplest choice of this filter function is a polynomial. This was used by Michel de Ferrara and co-authors in his famous paper on ChebNet. So they used a polynomial filter. Here, the parameters of the filter are the coefficients of the polynomial. And you can compute it efficiently, avoiding the graph Fourier transform altogether. You just take the powers of the Laplacian. And because the Laplacian is usually a sparse matrix, it is as sparse as the number of edges in the graph, you will get a complexity of equal to the number of edges, which is in many cases roughly equal to the number of nodes in the graph, if the graph is sparsely connected. Another important property that the Laplacian is a local operator. It affects only the neighbors. So the p power of the Laplacian will affect p hop neighbors. So as a result, the filters will be localized. We can also show generalization, as I mentioned before. We can apply this polynomial to any operator. It can be adjacency matrix, it can be Laplacian. And we don't really care whether the matrix is symmetric or not, because we are not doing any explicit eigendecomposition. So it works equally well for directed graphs. Okay. So that was the spectral generalization of convolution using exactly the same principles that we've seen before. Now, usually some references in this field distinguish between spatial and spectral convolution. I find this distinction very artificial because, as you've seen, there is nothing spectral in, for example, this application of a polynomial. So let me reiterate this point. So again, if we look at the ring graph that models our one-dimensional grid with periodic boundary conditions, we've seen that this is the adjacency matrix of this graph is the shift operator. I can think of convolution differently, right? I can think of it as a linear combination of shifted versions of a diagonal matrix, right? Or the adjacency matrix of the graph. So here I have the main diagonal will be identity, right? So that's the zeroth power of A, the adjacency matrix. The second diagonal will be the adjacency matrix to power 1, then adjacency matrix squared, and so on. And I combine it with different weights, I get back this circulant convolution matrix. So essentially, this is a polynomial that we've seen before, right? Polynomial in A. So you see that this is a completely spatial construction that we can relate to the previous construction that we derived from spectral considerations as a spectral transfer function. So basically, these two views are the same way as we had them in the Euclidean case are exactly the same. Now, if I now arrange my node features in the graph into a matrix, and again, this requires fixing some order of the nodes, every row of this matrix represents a feature of the node. So here is, for example, the feature of the 6th node. So I can do two different things on this feature matrix. I can transform the features independently in each node. And this, in the simplest case, if it's linear transformation, I can write it as right side multiplication by a matrix, right? So when I multiply my feature matrix from the right, I transform each node feature vector independently. And I can also mix them. So it's usually it is called diffusion or propagation or message passing. So basically here I'm combining the features in adjacent nodes. So the graph diffusion, the operator, the matrix by which I multiply from the left can be many different things. So it can be the adjacency matrix. Usually it also involves some form of self-adjacency. So I add back the feature of the node itself. It can be the graph Laplacian, or it can be different variations of the two. And this gives rise to the simplest form of convolutional graphs that is called GCN, or graph convolutional network, work by Kipf and Welling. So this is the analogy of a convolutional layer in CNN. So I have the diffusion and the node-wise transformation followed by some nonlinearity. And if you want to make a deeper architecture, you combine several such layers. So here is a two-layer architecture that, for example, classifies nodes on this graph. So going back to our analogy between images and graphs, so we've seen that we started with very different structures and we ended up with rather similar constructions where we have some local aggregation of features on adjacent nodes, with the difference that in images the number in the ordering of neighbors is fixed. On graphs it is not fixed and the ordering is unknown. But in both cases we can do it efficiently with order of n complexity. So just to say a few words about pooling. So pooling in images usually is some form of reduction of the resolution of the image with usually nonlinear aggregation of the features. So in graphs, the analogy would be graph coarsening, where we collapse, for example, pairs of nodes in a graph and aggregate the features. Probably the special thing that can be done in graphs is that the way that this collapsing is done can be learnable. And usually the signal, the supervision signal of the downstream task is not enough. So usually you need to add some auxiliary losses, something similar usually to graph cuts or similar things. So if we look at the higher level at this recipe for doing convolution-like filtering on graphs, you see that what we've done so far is basically a very simple principle. So we can think of it as a linear aggregation of our node features, that the aggregation operation itself, it depends on some parameters, maybe something like linear combination of powers of adjacency matrix, like in polynomial filters, but not on the features. And this was the foundation of some early works on graph neural networks, such as ChebNet, GCN, and so on. We can make it slightly more interesting, so we can still make it a linear combination, but dependent on the features now, and that's the blueprint of architecture such as Monet or graph attention networks, where in Monet we construct a local system of coordinates where we use some Gaussian or other blobs to aggregate the local features. And basically we have learnable coefficients that depend on the structure of the graph and the features themselves potentially to aggregate the features in adjacent nodes. In graph attention, maybe this is even better crystallized in the form of learnable interactions between neighbor nodes and the node itself in which the aggregation is performed. And finally, this operation can be done completely non-linearly. So we have the most general architecture that is called message passing neural networks or edge convolution. That is probably the most general blueprint for these kind of architectures. Apologize, guys, my son is here. I told my son that if he comes, he needs to carry on with this talk in my place.
No problem at all.
So right, so basically this is the generic recipe for doing aggregation on graphs. So we have two operations. We have aggregation of the neighbors, which is done by some permutation invariant function, because again, I remind you, we don't have an order of the nodes in the neighborhood, which in the most general case looks at both the node features and potentially if there are also edge features. And then we update the current features of the current node. Now, the choice of the aggregation function seems to be very important. And let me visualize it with this example. So the black node is the node at which I'm updating the features, and the colors represent features in the different features in the neighborhood of this node. So you see that in this graph we have two identical features, the red features, and one green feature. So if I use the maximum, for example, which is a permutation invariant function, we cannot distinguish between these two structures, right? The maximum will not care how many times the same value appears. But if I use mean, for example, I would be able to tell them apart. On the other hand, if I have this graph, which has the same nodes twice versus the same node once, the mean will not care about how many times the same value appears, but the sum will be able to distinguish between them, right? So the bottom line is that the choice of this function is important, and it's probably appropriate at this point to ask the question, what is the expressive power of graph neural networks? And it is an interesting question because here we have both structure on the nodes on the graph and the graph itself. So in the case of Euclidean data, in the case of grids such as classical perceptrons, for example, it is much easier to pose it as a question in function approximation. So we can take the usual results that are formulated there is a form of density result. So we can say that the class of functions that can be represented by this architecture is dense in, let's say, the space of continuous functions. So here we need to account for the structure of the graph. And one way to go is to relate to what is called the graph isomorphism test. So to remind you, what is two graphs are told to be isomorphic if they have the same structure up to permutation of nodes. So if, in other words, if I can find an edge-preserving bijection between these two graphs. Now, interestingly enough, this problem of determining whether two graphs are isomorphic or not, we don't even know its complexity. So we know that it's not polynomial, at least currently there is no known polynomial time algorithm, but it's also not NP-hard. So usually it's put in a complexity of its own class that is called GI class. So a classical work by Lehman and Maurice Weisfeiler that actually thought to have invented a polynomial time algorithm for testing isomorphism of graphs tries to do some form of color refinement. So by color, I mean discrete labels of the nodes. So you start with a graph for which all the nodes are colored in the same way. And you look at the neighbors of a node. So if you look at the neighbors, at the features in the neighbors, they form what is called a multiset because the same element can be repeated more than once. And if you apply to it some injective functions, so think of some form of hashing that assigns a unique label to each such multiset, you get a color refinement. So here, for example, initially I have two types of neighborhoods where I have two neighbors and three neighbors on this graph, right? So they will be colored in a different way. So now I can repeat this process, and now I have three types of neighborhoods, right, that are shown here. So I can further refine the colors, but at the next iteration, the color will not change. So at this point, I stop and I produce the histogram of these different colors or discrete labels. I can do the same process for another graph. And if I get a different distribution of colors, I can for sure say that the graphs are not isomorphic. But if the colors are the same, I actually don't know. They are possibly isomorphic. So it's a necessary but insufficient condition. And in fact, we know that there are some very simple examples of graphs between which the WL test cannot distinguish. So they will they will produce the same distribution of colors. And one particular structure that Weisfeiler and Lehman cannot count is triangles, as shown here. So it is, on the one hand, it's surprisingly powerful because you can show that probabilistically almost all graphs can be distinguished by WL test. But on the other hand, it's very weak because even such simple structures cannot be distinguished. So what does it have to do with graphs, with graph neural networks? It was shown in two parallel papers that message passing is equivalent to color refinement. So graph neural networks are at most as powerful as the WL test. So this answers the question how powerful graph neural networks are. It has to do with the choice of the aggregation function. It must be an injective function. And it should be noted that in graph theory, WL test is not actually a single test, it's a hierarchy of tests, what is called KWL test, that look at k tuples of nodes. They're high dimensional, they are non-local, and it is possible to design equivalent high dimensional graph neural networks, which unfortunately have much higher complexity. So the best 3WL equivalent GNN that I am aware of has squared complexity in space and cubic complexity in time. So it's not very practical, but at least in principle, it's more powerful. Now, a different approach would be the following. So if we know that the WL test cannot detect certain structures, we can actually pre-count them and provide them in the form of some kind of positional or structural encoding or structural descriptor to the message passing algorithm. So with this architecture, the neural network is exactly the same. It just takes some extra features from the nodes or from the edges, and it's local and linear complexity. All the complexity is absorbed in the pre-computation, which in the worst case can be as bad as k-dimensional WL test, but in practice, for certain structures and for most graphs that are not fully connected, it is way more optimistic. And we see that we can show that we are strictly more powerful than WL, and we can always find examples on which KWL fails. These are usually graphs with strong regularity, whereas if we take the structures that this test cannot detect and explicitly count it, we can make a neural network that is strictly more powerful than KWL test. And we can use this as an inductive bias for different problems. And here I show you an example. So this is from standard benchmarks on which graph neural networks are evaluated. So here we have different graphs from the domain of chemistry and domain of social networks. And you see that there are prominent structures in both of these domains. So in social networks, for example, these are triangles and cliques that appear prominently. And by injecting these kind of structures in the form of problem-specific inductive bias, we get significant improvement in performance. So maybe it's the best visualized with molecules, where if I account for case cycles or rings in molecules of size 5 or 6 or higher, I get significant boost in performance of of predicting molecular properties. And this is not surprising because in organic molecules, rings are a very prominent structure. For example, aromatic rings, or again, the molecule of caffeine, it has 6 and 5 ring structures. So this is a form of problem-specific inductive bias that if we know a priori these structures, we can inject them into our architecture. So I see that I don't have much time left, so let me briefly outline what is next in store for deep learning on graphs and what are the open and exciting problems that exist out there. So one thing that is obvious and that was crucial for the success of deep learning in computer vision was benchmarks and large data sets, such as ImageNet. So in graphs, now we have what is called the Open Graph Benchmark, which is probably more diverse and more interesting than ImageNet because there are many flavors and many settings of learning problems on graphs. Efficiency and scalability. So if we want industrial applications, such as in the domain of social networks, we need these graph learning algorithms to scale to gigantic graphs with hundreds of millions of nodes. It involves, interestingly, both software but also hardware. So recently, hardware companies, chip manufacturers, are interested in making the next generation of their processors to support these form of architectures because they are becoming more ubiquitous and prominent in different zoo of applications. Dynamic graphs. So this is also interesting application, especially in social networks, where the graph is not actually fixed. It is an asynchronous stream of events that delete or add nodes and edges in the graph. So we need to account for this temporal dynamic structure. It is interesting to talk about higher order structures, and I didn't mention it, but there are some limitations to the message passing architecture that looks at only at neighbors and basically nodes and edges. There have been forever, for 20 or 30 years, different approaches in topological data analysis that look at what is called simplicial complexes, which generalizes graphs and edges and graphs to triangles and simplices. And it is interesting that this field re-emerges now in the framework of deep learning on graphs, where you can create an end-to-end differentiable topological loss. So it will probably be one of the alternatives to message passing in the future. I should also say that also another old field of manifold learning or nonlinear dimensionality reduction that tried to take advantage of the structure of the data. So we have very high dimensional data, but in many cases, the intrinsic structure of the data is low dimensional. So manifold learning tried to capture it usually in the form of k-nearest neighbor graph that was then flattened or embedded into low dimensional space, and on which you then would apply something like clustering. So these methods never really worked well, at least in machine learning applications. They are still used for data visualization. The reason being that these steps were done independently. So you would first handcraft some features or some space in which to represent your data. Then you build the graph to represent it. Then you would apply some low dimensional embedding of this graph, and then you apply machine learning. So graph neural networks offer the possibility of doing everything end to end by basically building the graph on the fly in a problem-specific way that is optimal for the downstream task, and making it part of a single differentiable architecture. So I believe that this is also something that will emerge in the next year or two, the comeback a modern version of these methods. Another very cool direction, what Petr Veličković calls algorithmic reasoning. So the idea that you can think of graph neural networks as implementation of graph algorithms. So you can learn graph algorithms such as, for example, shortest path or similar algorithms by a graph neural network. And some algorithms are very suited for graph neural networks because they have local structure and polynomial complexity. But you can also think of graphs as models for some complex physical systems, such as, for example, multi-particle systems in classical mechanics or in particle physics. And the edges can represent certain interactions. So if you use some learned function on these edges and you infer an equation from it, so a symbolic model, and you replace the learned generic model with an equation, you actually get significantly better generalization. And it is also much more interpretable and much more explainable. So that was very cool work from Kyle Cranmer and co-authors this year, where they used graph neural networks to learn symbolic representation, or basically physical formula of complex systems. And in a sense, maybe as a far-fetched goal, I would see that finally this reconciliation between deep learning community, let's say represented by Joshua Benjo, and the symbolic community represented by, let's say, Gary Marcos as a placeholder, could be at least to some extent reconciled with these methods. So I think this is very interesting direction. Finally, there are some interesting questions about theoretical properties of graph neural networks. So the expressive power was one of them. I think we just scratched the tip of the iceberg. Probably the more interesting direction that has been very scarcely addressed so far is the generalization capability. And this usually goes hand in hand, because you might have a graph neural network. So if you think of positional encoding, you can have unique identifiers, for example, some random vectors that you attach to your nodes of your graph, and they will characterize uniquely the nodes. So you will be able to do the message passing function that is adapted for every node of the graph. But of course, there is no way whatsoever to make the construction of these random features repeatable on different graphs. So there is trade-off between expressive power and generalization, and the structural descriptors seem to be a good halfway through between, on the one hand, expressive features, on the other hand, features that can be reproduced on other graphs. And again, some rigorous analysis of how these methods generalize is still missing. The last thing is killer apps, and unfortunately I don't have much time, so let me just mention briefly. Well, this year graph neural networks were one of the hottest topic in machine learning, and not surprisingly, because graphs are really very abstract models of systems of relations and interactions. You can apply them at all scales. So if you think of large scales such as social networks, which model interactions between people, we can apply them at the level of interactions between small things like molecules or metabolites or proteins. So they can model living organisms, or they can be applied at the very lowest level of chemistry, basically modeling molecules. And they are probably, that's the most prominent topic nowadays that is most promising. And this is really what worked well this year. So allow me to skip some results here. So there are two cover papers that appeared on the cover of major biological journals. One of them, Cell, that was the paper on using graph neural networks for discovery of new classes of antibiotics. Another one was on proteins. That was a paper in which I was a co-author that appeared on the cover of Nature Methods, where we used geometric deep learning to predict interaction and binding of proteins modeled as surfaces. So I think this itself is quite a record this year, that these methods are already becoming, if not real, but at least sufficiently interesting to pass the bar or certain level of convincing the domain experts in the domains of fundamental science, such as biochemistry and structural biology. And probably we'll see more results in that direction this year. So I believe in in the interest of time, I will probably stop here and will be glad to answer questions.